CS407 Numerical Analysis, Section 6.2 Natural Cubic Splines. So last time we looked at first and second degree splines, and they were pretty fun and allowed us to do some pretty cool approximations of curves. We found that they were useful in certain applications, but they generally do have a problem. In particular, the lower order derivatives are discontinuous, and that makes for a lack of smoothness, particularly for the first order linear splines, which were, kind of gave us those jagged curves that we drew with the ruler. The second order splines have a discontinuity at the second derivative, and the lack of smoothness is not as evident. Still, the curvature of the quadratic spline tends to change abruptly at each knot, so the curve may not be as pleasing to the eyes as we would like. So let's take a look at a definition for a spline of degree k, and this is the general definition of spline functions of arbitrary degree. So a function s is called a spline function of degree k if the domain of s is an interval in AB, s prime, s double prime, and the k minus first derivative of s are all continuous functions on that interval AB, and the knots are present such that the polynomial s of degree at most k on each subinterval ti plus 1. So basically we have the last condition says there are points t sub I that forms the knots, and that those are in fact ordered, and s is a polynomial degree k for each of the individual subintervals between those knots. Observe that no mention has been made of interpolation in the definition of a spline function. Indeed, splines are such versatile functions that they have many applications other than interpolation. Now, from the definition of spline function of degree k, we can see that the function will be continuous and have continuous derivatives all the way to the k minus first derivative. Higher degree splines are used whenever more smoothness is needed in the approximating function. Now, if we want the approximating spline to have a continuous mth derivative, a spline of degree at least m plus 1 is selected. To see why, consider a situation in which the knots t0 through tn have been prescribed. Suppose that a piecewise polynomial of degree m is to be defined, with its pieces joined at the knots in such a way that the resulting spline has m continuous derivatives. At a typical interior knot t, we have the following circumstances. To the left of t, s of x is equal to p of x. To the right of t, s of x is equal to q of x, where p and q are nth degree polynomials. The continuity of the nth derivative implies the continuity of the lower order derivative. So if the mth one is continuous, then the m minus first one is continuous, and the m minus 2 derivative is continuous. So at a knot t, the limit from both the left and right hand sides of the kth derivative of x are going to be equal, and likewise p and q, the derivatives for those two functions, the kth derivatives of p and q, are also going to be equal to one another. Since p and q are polynomials, their derivatives of all orders are continuous, and so the kth derivative of p is equal to the kth derivative of q. The last condition forces p and q to be the same polynomial because of Taylor's theorem. This argument can be applied at each of the interior knots, t1, t2, t to the m minus 1, and we see that s is simply one polynomial throughout the entire interval from t0 to tn. Thus, we need a piecewise polynomial of degree m plus 1 with at most m continuous derivatives to have a spline function that is not just a single polynomial throughout the entire interval. We already know that ordinary polynomials do not serve well in curve fitting. Cubic splines are the most frequent choice of degree for spline functions. 1 and 2 we've already seen. Cubic splines are the most frequent, and we don't actually need to go higher order. Basically, we can join cubic polynomials together in such a way that the resulting spline function has two continuous derivatives everywhere. And then we can impose 3 continuity conditions at each knot. Now, since s, s prime, and s double prime are continuous, the graph of the function will appear smooth. Discontinuities, of course, will occur at the third derivative, but these cannot be easily detected visually, which is one reason for choosing degree 3. Only highly trained dogs and mathematicians who are trained to sniff out these anomalies can actually detect them. Experience has shown that using splines of degree greater than 3 seldom yields any advantages. For technical reasons, odd degree splines behave better than even degrees, especially when interpolating at the knots. Finally, there's a very elegant theorem that we'll look at later that shows that in a certain precise sense, cubic interpolating spline function is the best interpolating function available. So our emphasis on cubic splines is well justified. So let's take a look at them. So for natural cubic splines, we want to interpolate a table of function values with a cubic spline whose knots coincide with the independent variables in the table. Here the t sub i's in this table are the knots, and we're going to assume that they're arranged in ascending order. The function s that we wish to construct consists of n cubic polynomial pieces, and the interpolation conditions s of t sub I is equal to y sub I. So basically it takes on those values at the knot that we specified in the table. In this formula, s sub I denotes the cubic polynomial that will be used on the subinterval ti plus 1. Continuity conditions are imposed only at the interior knots. That is t1 through tn minus 1. In this formula, s sub I denotes the cubic polynomial that will be used on the interval ti plus 1. And you can see here's the form of the cubic polynomial, the interpolating spline function s over on the right. The interpolation conditions are s of t sub I is equal to y sub I for 0 through n for I, and basically the left and right limits of the kth derivatives at values x are going to be equal. We're going to impose two more conditions, namely the second derivative taken at t0 and the second derivative taken at tn are both going to be 0. The resulting spline function is termed a natural cubic spline. There are additional ways to close the system of equation for spline coefficients, and these are periodic cubic splines and clamped cubic splines. A clamped cubic spline is a spline whose slope is fixed at both endpoints, and a periodic one is one that has the same values at the beginning point t0 as those at the endpoint tn. For all continuous differentiable functions, clamped and natural cubic splines yield the least oscillations about the function f that it interpolates. So let's take a look at the number of conditions. There are n plus 1 knots in these cubic splines, and hence n subintervals. On each of these subintervals, we have a different cubic polynomial. Cubic polynomials have 4 coefficients, so we have a total of 4 n coefficients. Now, within each subinterval, the interpolating polynomial must go through 2 points, which give it 2 n conditions. The first and second derivatives need to be continuous at the interior point, and that gives us 2n minus 1 more conditions. And the second derivatives must vanish at the 2n points. So the sum total of this is 2n plus 2 times n minus 1 plus 2, which yields a total of 4 conditions, which is what we need for the cubic polynomial. Let's take a look at an example. So here what we want to do is derive the equations of the natural cubic interpolating spline for the following table. So minus 1, 1, 0, 2, and 1, 1. So what we need to do is we need to define parameters a, b, c, d, e, f, g, and h so that s of sx is a natural cubic spline. And it's going to have this form. Well, from these interpolation conditions, we have s minus 1 is equal to s0 at minus 1, which is minus a plus b minus c plus d, and that's equal to 1. And then s0, and again we get that 1 from the table, and we get the form a, b, c, d, or minus a plus b minus c plus d from the equation there. S of 0 is going to be s0 of 0, which means d is equal to 2 from the table. S0 is equal to S1 of 0, which is equal to H, which is equal to 2, and S1 of 1 is S1 evaluated at 1, which means E plus F plus G plus H is equal to minus 1. Now, we take the first derivative and the second derivative of S of x, and we need to do that piecewise in terms of the differentiation. And from the continuity condition on S prime, we have S0 prime at 0 is equal to S1 prime at 0, which means that C is going to be equal to G. From the continuity condition on S double prime, we have S0 double prime at 0 is equal to S1 double prime at 0, which is going to give B is equal to F. And for the natural cubic spline condition, S0 double prime evaluated at minus 1 is equal to 0, and S1 double prime at 1 is equal to 0. So we get 3a is equal to b, and 3e is equal to minus f. We can put these into a system of linear equations and solve them to get a is equal to minus 1, b is minus 3, c is equal to minus 1, d is equal to 2, e equals 1, f minus 3, g minus 1, and h2. We take those and we plug those back into the original equation that we had on the previous slide, and that gives us our cubic spline. Let's take a look at an algorithm to make natural cubic splines. So, from the previous example, it's pretty evident that we're going to need to develop a systemic procedure for determining the formula of a natural cubic spline, given a table of interpolation values. This is our objective in the material on the next several slides. Now, we can start out and we know that S double prime is continuous. So the number Z sub I is equal to S double prime Ti for 0 through n are unambiguously defined. We don't know the interior ones, but we do know Z0 is equal to Zn is equal to 0. Once we know all the Z sub i's, we can construct S. So on the interval Ti plus 1, S double prime is a linear polynomial that takes the values Z sub I and Z sub I plus 1. So we can give Si double prime of x the following form, and with H sub I is equal to T sub I plus 1. Notice that S sub I double prime T sub I is equal to Z sub I, and Si double prime at Ti plus 1 is equal to Zi plus 1, and Si double prime is linear. If we integrate twice, we get S sub I of x. From the previous example, it's evident that we need to develop a systemic reading my script twice there. So let's continue on with our algorithm for natural cubic splines. So by adjusting these integration constants, we obtain a form for S sub I that is easier to work with, namely S sub I of x is equal to the following equation, which is probably written in the Black Speech of Mordor, and I won't read it aloud here. After we get that form, it's going to be a little bit easier for us to work with after we get the Z sub i's. We can impose the interpolation conditions Si of Ti is equal to Yi, and Si T sub I plus 1 is equal to Yi plus 1, and determine C sub I and D sub I. Notice that if we differentiate the first equation twice, we end up with the second derivative that was shown on the previous slide. And when the Z sub I values have been determined, the spline function S of x is obtained from the equations of the form S0x, S1x, Sn minus 1x. Now all that needs to be done is to determine the Z sub i's. So we also need to have S prime be continuous. So at the interior knots, we want S prime I minus 1 T sub I is equal to S prime I evaluated at Ti. So again, we have this form for Si prime of x, and that means that Si prime evaluate T sub I is going to be this, and S prime I minus 1 at Ti is this. When we set them equal to each other, we get another equation. Now, the figure on the right is a cubic spline with adjacent pieces of Si minus 1 and Si. And basically that shows the bullet point 1, which means we have S prime continuous. So basically what we end up having is we have the equation developed on the last slide, and by letting u sub I equal 2hi minus 1 plus h sub I, and vi is equal to 6 times bi minus 1, what we get is we get a nice tridiagonal system. Now I know these are your favorites and you already have the code to solve them. We're going to see a different technique this time around though. Note that the simplicity of the first and last equation is a result of the natural cubic spline conditions. S double prime evaluate at t0 is equal to S double prime evaluate at tn is equal to 0. So z0 is 0 and z sub n is equal to 0. Let's look at another example. So example 2 asks us to repeat the same problem we had with example 1 using the natural cubic spline algorithm with points minus 1, 1, 0, 2, and 1, minus 1. From these values, we can start by labeling the t sub I and the y sub i's. So t0 is minus 1, t1 is 0, and t2 is 1. y0 is 1, y1 is 2, and y2 is minus 1. So we can then obtain h sub 0 and h sub 1, which are t1 minus t0, 1, and t2 minus t1, which are 1. So both h's are 1s. From there we can obtain b0, which is 1, and b1, which is minus 3. And then using the formula we developed on the last slide, we can get u1 and v1. u1 is 4, and v1 is minus 24. After getting those values, we can put them together in the tridiagonal system that we defined, and we can solve that tridiagonal system to get z sub 0 is 0, z1 is minus 6, and z2 is 0. And plug those back into the original equation, and we get a curve of the form shown here. S0x is minus x cubed minus 3x squared minus x plus 2 on the interval minus 1, 0, and x cubed minus 3x squared minus x plus 2 on the interval from 0 to 1. The figure shows the natural cubic spline for both examples 1 and 2. That's one smooth curve. Now let's see how to deal with those tridiagonal systems. So consider the tridiagonal systems that we end up getting for these natural cubic splines, shown in bullet point 1. Basically, the first and last conditions are the nice one that we get from the definition of natural cubic splines, and we can actually eliminate those, and we end up with a symmetric tridiagonal system of order n minus 1. So, as you know from chapter 2.3, we can use the trie procedure to solve this system, but let's see if we can make things more efficient. In particular, in Gaussian elimination without pivoting, we get the following u sub I and v sub I values. And back substitution would then allow us to find the z sub i's. We can put these two steps together to get the algorithm to solve the natural cubic spline tridiagonal systems directly instead of using the trie procedure. So here is the algorithm. Basically, given the interpolation points ti, y sub I, we compute h sub I and b sub I, and then find u1, v1, and then compute inductively for I equal 2 through n minus 1 the u sub I and v sub I values. Then we find z sub n, z sub 0, and then compute all the other z sub i's inductively. Now, the algorithm could conceivably fail because of divisions by 0. However, it's possible to show that the u sub i's are not going to be 0 for all of the i's. The final nested multiplication form of s sub I x is given down here at the bottom. You can also find this on page 270 of the text. The nested format is going to make it easier to evaluate. We now turn our attention to the pseudocode for natural cubic splines, and there are going to be quite a few different procedures for this. In particular, we can now write routines for determining a natural cubic spline based on a table of values and for evaluating this function at a given value. First, we use algorithm 1 for directly solving the tridiagonal system. This procedure, spline 3 coefficient, takes n plus 1 table values given by t sub I and y sub I and computes the z sub i's and stores them in the appropriate array. We also have intermediate working arrays for h sub I, b sub I, u sub I, and v sub I. Now, after getting the coefficients, we have a function called spline 3 eval, and that's written for evaluating an SN multiplication form, Sx for the cubic equation for a given x. The procedure spline 3 eval first determines the interval ti plus 1 that contains x, and then evaluates s sub I x using the nested form of the cubic polynomial. The function spline 3 eval can be used repeatedly with different values of x after one call to the procedure spline 3 coefficient. For example, this would be the procedure when plotting a natural cubic spline curve. Since procedure spline 3 coefficient stores the solution of the tridiagonal system corresponding to a particular spline function in the array, the arguments n, t sub I, y sub I, and z sub I must not be altered between repeated uses of spline 3 evaluation. As an example, we can write the pseudocode for a program that determines the natural cubic spline interpolant for sine x at 10 equidistant knots in the interval from 0 to 1.6875. Now, we've done that problem before with interpolation, but here we're going to use a natural cubic spline. Over the same interval, we subdivide each interval into 4 equally spaced parts and find the point where the value sine x minus s sub x, which is the interpolating cubic spline, is largest. So here's the driver code for this that you would put into the program. The output is going to be j is equal to 19, x is equal to 0.890625, and d is equal to 0.93 times 10 to the minus 5. We can also use mathematical software such as MATLAB to plot the cubic spline curve for this data. But note that the MATLAB routine for spline uses the not a knot end condition, which is different from the natural end condition that we're using. This not a knot condition dictates that s triple prime be a single constant in the first two subintervals and another single constant in the last two subintervals. Tools such as Mathematica and Maple can be used to plot cubic splines, but let's take a look at the general process for plotting them. So let's look at the use of spline functions for fitting a curve to a set of data. Consider the following set of data in the table. Now, these 20 points were selected from a wiggly freehand curve and were selected at points where the curve bent sharply. We can actually use cubic splines to plot these, and this curve shows the results of using a natural cubic spline with the help of the routines we developed in this section to plot the points in that table. Note it turned out pretty nicely, and math software can also help you with this sort of task to plot them. Now, in 2 dimensions you have something called space curves. So 2 cubic spline functions can be used together to form a parametric representation of a complicated curve that twists and turns. Select points on the curve and label them t equals 0, 1 through n. So t is equal to 0 through n. For each t, read off the x and y coordinates of the point, producing a table. We then fit x is equal to st and y is equal to s hat t, where s bar are natural cubic spline interpolants, which gives a parametric representation of the curve. Now we can see this in action when we select 13 points on the well-known serpentine curve given by y is equal to x divided by 1/4 plus x squared. So the knots won't be equally spaced. We can write the curve in parametric form where x is equal to 1/2 tangent theta and y is equal to sine 2 theta. We take theta is equal to I times pi divided by 14, where I runs from -6 to +6. We can then plot the natural cubic spline and interpolation polynomial for this. So Here you can see the cubic spline, which is the solid curve, and the polynomial curve, which is the dotted one. This is an example of curve fitting using both, and we used our routines coef and eval, as well as the cubic spline routines spline 3 coef and spline 3 eval. Figure shows the resulting cubic spline curve and the high degree polynomial curve from an automatic plotter. The polynomial becomes extremely erratic after the fourth knot from the origin and oscillates wildly, whereas the spline is nearly a perfect match to T. Now, 1 is good, but 2 is better. So here we have an example where the curve is continuous, but its slope is not. And we kind of run into this before. So what we do is we use two cubic splines. One runs between 0 and 4, and the other runs between 4 to 7. And the two curves in this graph will have two different slopes, but they go together to make a cubic spline. So why are splines so smooth, or are they? So why do spline functions serve the needs of data fitting better than ordinary polynomials? Well, to answer this, we should understand that interpolation by polynomials of high degree is often unsatisfactory because polynomials may exhibit wild oscillations. Polynomials are smooth in the technical sense of possessing continuous derivatives of all orders, whereas in this sense, spline functions are not smooth because we can only go to so many derivatives. So a little bit of trickiness with the definition of smooth. So wild oscillations in a function, particularly polynomial interpolation, can be attributed to its derivatives being very large. Consider the function whose graph is shown in the figure here. Now, the slope of the chord that joins P and Q is very large in magnitude. By the mean value theorem, the slope of that chord is the value of the derivative at some point between P and Q. Thus, the derivative must attain large values. Indeed, somewhere on the curve between P and Q, there's a point where f prime of x is large and negative. Similarly, between Q and R, there's a point where f prime of x is large and positive. Hence, there's a point on the curve between P and R where f double prime of x is large. The reasoning can be continued to higher derivatives if there are more oscillations. This is the behavior that spline functions do not exhibit. In fact, the following results show that at a certain point of view, natural cubic splines are the best functions to use for curve fitting. So, theorem 1 is the cubic spline smoothness theorem, and the interpretation of the integral inequality in this theorem is that the average value of the absolute value of s double prime of x squared on the interval AB is never larger than the average value of this expression with any twice continuous function f that agrees with s at the knots. So, basically, the quantity absolute value of s double prime of x squared is closely related to the curvature of f. Next time we'll take a look at an overview of B-splines.